You press the power button. The display lights up. You push the throttle lever, but the wheel refuses to move. The battery registers a full charge, and the digital systems are completely awake, yet the vehicle itself is physically paralyzed. An unresponsive scooter rarely means the entire machine is dead. These failures almost always fall into one of two distinct categories. The first is the false alarm. This happens when the scooter's internal safety overrides are actively and intentionally cutting the power. The second is the fatal flaw, a physical break or a burnt component somewhere inside the electrical powertrain. Differentiating between a safety override and a physical hardware failure allows for a logical, systematic isolation of the fault. The primary suspect for a false alarm is the brake sensor. Electric scooters use a built-in safety mechanism where pulling the brake lever immediately cuts all motor power and engages regenerative braking.
A physical issue, like a stuck, misaligned, or overly tight brake cable, holds that sensor open. It tricks the scooter's computer into believing the brakes are constantly applied. Check the digital display. A warning indicator, such as a red exclamation point, confirms that this mechanical safety override is active. Fixing this requires a physical adjustment. On hydraulic brake levers, you loosen the small lock screw securing the sensor, then carefully unscrew the sensor body by a few turns to relieve the pressure. Verifying these mechanical flags first saves hours of unnecessary electrical teardowns and parts ordering. Once the safety overrides are ruled out, the focus shifts to the origin of the movement signal, the throttle assembly. Tracking the signal from the rider's hand requires a digital multimeter to measure the specific voltage output at the wiring connectors. Set up the multimeter by placing the black probe into the COM port and the red probe into the voltage port. Inside the throttle wiring, pellers dictate function. The red wire delivers 5 volts of power, the black wire serves as the ground, and a white or green wire carries the active signal. We start with a baseline reading. Measure the DC voltage between the signal wire and the ground wire while the throttle sits completely at rest. A healthy throttle will show a baseline voltage sitting exactly between 0.85 and 1 volt without any physical pressure applied. Next is the dynamic test. Slowly twist the throttle. The voltage should climb smoothly, peaking around 4.5 volts at maximum compression. A static, unchanging voltage reading during this test completely isolates the throttle as the dead link. It requires a direct replacement. When the throttle data is healthy, we move deeper into the internal hardware to look for physical component failures within the motor controller. This schematic shows the complexity of the controller's routing, mapping exactly how power and data distribute across the entire chassis. The critical section responsible for physical movement relies on the thick phase wires, typically yellow, blue, and green. These deliver raw power directly to the motor. The controller manages this massive current using components called MOSFETs. These act as high-speed electronic valves, rapidly opening and closing to push power down those 3 distinct channels. When a MOSFET blows, it creates a magnetic short. If you spin the unpowered wheel by hand, you will feel a heavy, stuttering mechanical resistance. We test for this failure by switching the multimeter dial to the continuity or 200 ohm testing mode. Probe the metallic pins inside the Anderson connectors. You are checking each of the 3 phase wires against the main red and black power lines. A healthy motor controller will show a significant amount of electrical resistance during this check, usually measuring in the kiloohms. Finding a zero resistance short during this specific test pinpoints a fried MOSFET. The motor itself might be intact, but the logic board driving it is broken. The final stage of the signal chain is the wheel hub itself and its internal Hall sensors. A Hall sensor acts as a magnetic switch. As the rotor spins, magnets pass closely by these stationary sensors, telling the controller the exact physical position of the wheel so it knows precisely when to fire power. A failed sensor creates chaotic physical symptoms. The motor receives power, but it stutters violently, grinds loudly, or refuses to catch and rotate. We test this live by slowly turning the wheel by hand and watching the sensor's voltage on the multimeter. The reading should constantly alternate between 0 and 5 volts. A lack of voltage fluctuation confirms the sensor is dead. The controller is sending perfect signals, but the motor is completely blind to them. We started at the external mechanical safety overrides, moving down through the internal electronic logic checks, systematically checking the brake switches, verifying the throttle data, testing the MOSFET valves, and measuring the Hall sensors eliminates guesswork entirely. Applying basic multimeter principles allows anyone to trace electrical faults directly to their source. A paralyzed electric vehicle is not a total loss, but a system of verifiable components that any writer can evaluate. Isolation of the failure leads directly to the solution.